Now I'm going to discuss the topic of recursion. So first, what is recursion? Recursion is when a function calls itself. So let's say I have this, int main, we'd have void in here really, f, let's say give it 5. And what I'm about to show you won't technically be correct for how we'd want to write this function, but I'm just demonstrating the calling itself part. So this function here I say is return type of void. There's an f, say int n, say it prints in, %d, maybe a new line, n, and then I do this, f of n minus 1. This is the recursive part, because what happens, we start at main, we call f with the value of 5, so we come into this, and this is all pushed onto the stack. If you don't know what the runtime stack is, look at one of my other videos, but this is pushed onto the stack with the value of 5. We print 5, and now I call f again with 4. So I get another instance of the function, this time with the value of 4. It prints 4. I call f again with the value of 3, so I get another instance of the function. So what's happening here, if we look at the stack, down here in main, we have f of 5, and then when I get here where I have f of 5, I call f of 4. When I get to f of 4, I call f of 3, and so forth. Now what makes this wrong is I don't have a stopping mechanism. So what keeps it from just doing this and blowing up? Well, nothing for the way this is written. So you really need to think about some way of saying, oh, you've reached a certain point, quit calling yourself. Otherwise you get what's called a stack overflow, just like the website Stack Overflow. So that's recursion right there. So let's look at some examples. Now I'm going to start off with two classic examples, factorials and the Fibonacci sequence. All right. So what I like about these examples is that they're easy to implement and they're also easy to understand. What I dislike about these examples is they're easy to replace and therefore you don't really need to use recursion. So they're really lousy examples of demonstrating the power of recursion. Right? Before we move on and talk more about that, let me explain what these are. Remember that factorials is that n factorial is defined to be the number n, because it's typically an integer, but technically you can define it for other real numbers. But n times n minus 1 times n minus 2 times ... times 1. Right? And the Fibonacci sequence typically starts off with 0 and 1, and then each additional number is the sum of the previous two numbers. 0 and 1 is 1, 1 and 1 is 2, 1 and 2 is 3, 2 and 3 is 5, 8, 13, 21, ... So if I don't think these particular examples are very good, why am I going to talk about them? Well, I think they make it easy for you to understand the process. Like this is easy to understand. And then eventually we need to know how to use recursion, because in the future videos I'm going to implement some data structures, and in order for us to process those data structures we really need to know how to use recursion. And if we don't, it would be very, very difficult to do what I want to do without using recursion. So overall though, why is recursion used? So one reason is what I just told you, make some things easier. Or easier to do. Another reason is some things are defined recursively. Those things. The Fibonacci sequence, how is it defined? Well, it's defined as this, that to get the Fibonacci number at index n, you just sum the two previous numbers. So if n is 10, f of 10 is equal to f of 9 plus f of 8. So this is a recursive definition. And therefore, it's easy to think about how I would program it this way. So a lot of people do that. And then the third reason is some programming languages actually don't have loops, but they expect you to use recursion to repeat processes. So some programming languages expect you to use it. All right. So let's write some code to see all that in action. And we'll start with factorial. So my function is this. It's going to return a number. Let's start with what the return type is. It turns out that producing factorials, if you haven't done that or haven't done much of it, you may not realize that factorials grow very large very quickly. And so you only have to get to around Fibonacci of 12 or 13 or 14 before the value is too large to fit into an int. Since they're all going to be positive numbers anyway, then I'm going to use an unsigned long as my return type. Right? So this is eventually what we'll return. And so if we think about it recursively, that is this, I'll just write this here, that we say that n factorial, which I said was equal to n times, I won't use parentheses here to make it easier to write, n minus 1 times n minus 2 times ... Right? The recursive definition is that n factorial is equal to n times n minus 1 factorial. Why is that? Because say, for example, if n was 4, 4 factorial is 4 times 3 times 2 times 1. Well, that's equivalent to saying 4 times 3 factorial, because 3 factorial is 3 times 2 times 1. So this is our recursive way of thinking about it. So that's what I'm going to implement. So I'm going to return n times factorial of n minus 1. All right, so are we done? No, because I don't have my stopping mechanism. So what is the stopping mechanism for this? Well, 0 factorial is defined to be 1. So that means if the number that I'm given is 0, then I just need to return 1. So why not just say 1, since if n equals 1, I also will return 1? Well, because then I can't deal with the case where n is equal to 0. So now I'm dealing with both. So that should be the whole definition. So let's look at some numbers here. I'm going to use a loop to test a whole bunch of numbers at once. 4, I is equal to 0. So test that first thing. I is less than 10, I plus plus. And we'll say that %d factorial is equal to %lu, which is for unsigned longs. That should still be backslash n. Zero factorial is 1, like it's supposed to be. 1 factorial is 1. 2 is 2 times 1. 3 is factorial is 3 times 2 times 1 is 6. 4 factorial is 4 times 3 is 12. Times 2 is 24. Times 1 is still 24, and so forth. So these are correct. All right. So that was the version that used recursion. But I could just actually replace that with a loop. Let's do this. Factorial 2. We'll still give n to n. Just so I don't forget, I'm going to go ahead and fix this. So how would we do this? Well, of course, if 3 factorial is 3 times 2 times 1, that's also equal to 1 times 2 times 3. So I need some way of keeping the product. So instead of writing 1 times 2 times 3, think of it as being like a sum. If I told you to sum the numbers 1, 2, 3, and 4, if you were using a loop to do that, you wouldn't say 1 plus 2 plus 3 plus 4. You'd say sum equals 0, and then you add 1 to it, and then you add 2 to that, add 3 to that, add 4 to that. Well, here, our product needs to use 1 instead of 0 as an initial value. So int prod equals 1. Sorry, equals 1. I also need variable I. And now I'm going to say 4. I is equal to 1. I is less than or equal to my input value of n, I plus plus. And actually my product is wrong. It should be an unsigned long. So I'm going to say product is equal to product times I. Return the product. And like I just said, this should be unsigned long, which is a type of int. But remember what this means? I don't have a sign bit anymore, which allows me to double my range of values, or excuse me, not my range, but my magnitude of the longest value. And long on my computer will be 8 bytes. So this allows me to create a huge number. So I think I'm using this one now, Factorial 2. Oops, what did I do wrong here? And got to end this. So it looks like the same numbers, right? And to prove I'm really here in this function, I'm here. So see, it does work. So which version should you use? Well, I mean, they're both about the same amount of work. So I don't know if there's anything to gain from using any particular version. Just pick one. It doesn't matter. Now let's see Fibonacci sequences. So let's do the same thing in terms of go through a sequence of numbers and see what we get. Fib of that is equal to, and this will just be an int because we'll have other problems long before we get to a value that's too large to store as an int, as we'll see. So this would be fib of I. So we'll return int fib and ultimately we're going to do this, return Fibonacci of the two previous numbers. All right, but what's our stopping mechanism? Well, the first two numbers in the sequence are 0 and 1, so they're defined to be f of 0 is 0 and f of 1 is 1. So we want to use if n is equal to 0 or n is equal to 1, then just return n. That way if the person puts an n, then I return 0, or excuse me, inputs 0, I return 0. They input 1, I return 1. I could have two different if statements, but this takes care of what I need. Let's see what this does. 0, 1. Add those together to get 1. 1 and 1 is 2. 1 and 2 is 3, and so forth. So that's correct. So what's the problem here? Well, let's do this. I'm going to change this up slightly to where I get rid of the loop so I can look at specific values. So let's do 20. So I assume that's correct. We would have to look that up since I would actually need a program to do that for me. Let's try 30. All right, 832,000. Well, an int can store plus or minus 2 billion or so, a little bit more than that. So that's not a problem. So what's the issue with doing this? Wow, that took a little while to run, right? Let's try this. 45. Is the problem that the number's too big? No, that's 102 million. So what's happening? Well, my computer's really working. It's really trying to produce Fibonacci of 45, which I have to assume is correct. So what is this number? 3 digits, 3 digits, 3 more digits, so it's 1.1 billion. So that's less than the slightly over 2 billion that I can store. But notice it took a little while to do that. And so why is that? Well, this is, for this particular implementation, there are fast ways to do this, but for this implementation, there's an issue. So let's see what that is. So let's do Fibonacci of 4, and then explain how it works. So it's 3. So what happens when I say I want Fibonacci of 4? Well, remember our definition. Get a different pen. That Fibonacci, or actually we normally write it this way, f of n is equal to f of n minus 1 plus f of n minus 2. So it means when I want f of 4, I need to produce f of 3 and f of 2 and add those together to get this. But to get f of 3, I need f of 2 and f of 1. To get f of 2, I need f of 1 and f of 0. And then right here is another f of 2, so that's different. So this one also needs f of 1 and f of 0. And then these values are, this is 0, this is 1, this is 1, 0, 1, and so 1 plus 1 plus 1 is 3, which is the answer we got. So look at this tree. This is really starting to get big very quickly. And imagine I really went to f of 5. Well, if I had f of 5 here, it would need f of 4 and then also f of 3. And the f of 3 is this entire subtree, so I'd have to produce that again unless I save the results. And that's actually the solution to this problem. Save the results and check to see if you've already done it. So if I get to right here, and depending on how you coded it, really it would reach this f of 3 before this one. But whichever one it reaches second, you should look up in a table and say, oh, I've already figured out what this is. Now just plug that number in instead of going down the tree. So if we think about our stack, what is happening? Well, down here we're saying that I want f of 4. And so when I go into the function and write that I want f of 3, or then I'm returning f of 3 plus f of 2, the f of 3 is reached first, so that goes onto the stack. So this is f of 3, this is to produce f of 4, this is main. So f of 3 is f of 2 plus f of 1. So what happens? Well, it has to produce the f of 2 first. So now to get that, I need f of 1 plus f of 0. Well, to get f of 1, I have to go again. So here I'm just going to return 1. So then it returns back to where it came from, which is here. So it says now I get f of 0. And this actually would get popped off the stack because I reached the final return for that one. So now this would be f of 0. It would return 0 to here. Now I have 1 plus 0, so I can get 1. Well, this is popped off the stack to return to here. So now I know f of 2 is equal to 1, but I still don't know what f of 1 is from its perspective, so I have to do this again. See how this is blowing up? So this tree becomes huge for larger values of n. In fact, let's count what's happening and blow your mind on how many function calls I'm really making here. So let's create a counter, and I'm actually using a global variable here. So int counter equals 0, and every time I come into this function, I'm going to increment the counter first. It doesn't affect anything else I do, but then what's going to happen is I'm going to eventually say print %d function calls. where I use counter. So it says there are 9 function calls. Is that correct? Let's look over here. When we did f of 4, well, we entered the function the first time looking for f of 4. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9 function calls. Just to get f of 4. So you think, well, 4 versus 9, that's not that big a deal. But now let's go back and do something else, like say 10. That's 177 function calls. Just do Fibonacci 10. What about 20? 21,000 function calls. 30. 2.6 million or 2.7 million, close. And let's see what that 45 took that we were looking at earlier. In fact, this may be, it might be too big for an int. I don't actually know. We'll find out. One of the ways you would be clued in that you had exceeded the size would be this right here. See the negative number? How did I get a negative number when I'm always adding 1? Well, what happened is I incremented so many times I shoved the bits over to produce a negative number. Because remember, int is a signed integer. And so if the leading bit is a 1, that means it's a negative number. So this actually is wrong. This is claiming it's a negative number. So let's do this. Let's make this an unsigned long. And now I'm going to say LU here. I think this will be big enough. Takes a little while to run. And let's see how big that number is. 3.6 billion function calls to produce Fibonacci 45. That's why it takes so long to run. And I wouldn't even want to try to find Fibonacci of 50 or 60 or something like that. And even that, those numbers are starting to get pretty large. So if I want to try Fibonacci of 50 or certainly by 60, I would probably not use an int to store this. I probably would use an unsigned long for that as well. So that's the reason why it blows up. So that's another reason why recursion is bad if you do this. Now the solution, which I won't demonstrate here, is to save intermediate results and print those out. Or if all you care about is the final number, which is all I printed, you actually can avoid this by just writing a loop where you just go through and produce each of the numbers along the way yourself, just like you would by hand. That's actually an easy solution. So those are the possibilities. Let's look at some other examples that might make you more of a believer in the power of recursion and why we might use it. Let's do this. Char S. All right, there's a string. Now let's say I want to print that string. So of course that's easy enough to print. I want to print it character by character, so that would be easy enough to use a loop. But let's use recursion to do this. So I'm going to call the function print string or print chars and give it S. Now I could write it this way, char S, but it will help us understand it better. This doesn't actually affect how it works, but conceptually it makes more sense to me to do this. Now technically, and if you saw my video on pointers, in which I talk about how pointers and arrays aren't technically the same thing, this is an array, but this is a pointer. So even if I do this, the computer in this case turns this into a pointer. So I might do this to make it clear that I'm expecting an array of characters, or the address of an array of characters, I should say, but the computer treats it as if I had written this. So this really is a pointer, and the distinction is I can reassign this pointer. S here is not a pointer, so I can't reassign it, right? So that aside, let's see what I would do here. So what's my stopping mechanism? Well, what I want to do, well, we'll come back to the stopping mechanism. I want to print a character, and since T is the address of A to begin with, how do I print the A? Or how do I get the A character? Well, I need to dereference the T. So star T will be A in the first place. So %C, and I'm going to put a space here to make it clear that I'm just printing a character. So these will all be on the same line. And then we'll put a new line down here. And then how do I use recursion? Well, I want to move to the next address. So I'm going to say print chars. And I'm going to give it the address stored in T plus 1. So if the address is BF00 for the A, then the B will be BF01. So this adds 1 to it, and it comes in, and now it has the address of the B, so it can be printed. So what's my stopping mechanism? If star T, that's the value that T is currently pointing at, is equal to the terminating null, return nothing. Return like that. So let's see if this works, and then we'll see how this is useful beyond this. So there's my spaces, making it clear I'm printing each individual character. So you think, well, okay, I could have just written a loop to do that, right? I mean, what's the problem? But watch this. Swap these two lines. I just print it in reverse. What just happened? I'm taking advantage of the runtime stack. So how does that work? Let's use a little version of it to make it more clear, since I'm going to do it by hand. So there's my CBA, all right? So how does this work? So our string is ABC. And so initially, when I call the function, I give it the address of the A. So down here in main, what I'm really passing, and I'm just going to say F is the function, all right? What I'm passing is the address of the A character, right? So we get to this instance of the function where the value it received is A. And then what do? I essentially say F of the address of the B before I say print A. So when I get back, I'm going to do this, print, and I'm just simplifying here, print the A character. So then I call the function again. So this is F of, given the address of A really. So F of the address of B, so there's an address in here. So it receives the B, but then I say, here's the address of the C, and when you get back, print B, because that's what we were given. I get here, this is F of address of C. So this line is really over here. So what I do, I call it and I say F of the address of the terminating null. And when you get back, print the C. So we arrive at this point and we just return. Because at this point we had the address for the terminating null. So now we return to here. Well, we pick up where we left off. We left at this point where we passed the address of the character to the function. So by picking up where we left off, we print C. And then we're at the bottom of the loop, or excuse me, the function. So we return where we left off, which is right here. So what does it do next? It prints B. We're at the bottom of the function, return where we left off, which is here. It does the next thing, prints A. At the bottom of the function, return where we left off, which is here. We're at the bottom of the main. So we just printed CBA. And so by swapping these two lines, I can go back to just printing A before I call the function, print B before I call the function, print C before I call the function, and I get it the other way again. So could I avoid this? Sure, I could have something where maybe I use string length to find the length of the string, and then have a loop that counts down. So if this is really my string, the loop starts here and starts working its way back. Yeah, I could do that. But this was so simple just to flip the two lines. When we get to our other data structures, we'll see something similar to this, in which I won't be able to use a loop to print something in reverse, but by swapping a couple of lines of code, I'll print something in reverse. But we have to see that data structure first. So let me show you one last thing that I hope will make you a believer in the power of recursion, although it's something you should never do yourself. So there's a contest. Let me show you this before I leave. There's a contest called the Obfuscated C contest. And so to obfuscate is to hide the meaning of or make unclear. The purpose of the Obfuscated C contest is to write code that does something, but it's written in such a way that you can't tell what it's supposed to do. And some of them will really blow your mind. For example, there's one that's been formatted to look like a maze, and when you run it, it generates random mazes. But let me show you my favorite example from this contest, because it relies heavily on recursion, plus a lot of other things to hide its underlying purpose. All right. So Christmas.c is the name. This is the program. This is the whole thing. So where's the recursion? Here's main. Now this was written in the 1980s, I believe, but it still compiles as legal C89. Although I think newer versions of C make some of what's here illegal, or at least try to make you not do it. You really shouldn't write any code that looks like this. And I think actually what they did, because there's some websites devoted to sort of unraveling this, is that the person probably started with something that was easier to read, and then they found alternative ways to do the same thing that were less clear. So here's main calling itself, here's main calling itself, calling itself, calling itself, a bunch of other places. So there's all the recursion. Some of the other things they do to hide the meaning is, in my conditionals video, I talked about the ternary operator, which consists, basically looks something like this. You'd have some test condition, the question mark, what you want to do if true, colon, what to do if false. So it's basically, if test, do this, else do this. And so they've used that a lot throughout here. So you'll find a bunch of question marks. Here's one. There's another, because I have an embedded ternary operator or whatever. But this is the entire program right there. All right. So let me compile that. So I'm going to do C89 Christmas and then run it. That program produces the 12 Days of Christmas song. Believe it or not. Now how it works, I can't tell you really, because it's so cryptic that it amazes me at least. But this little amount of code using this much recursion produced this, plus a lot of other magical things, right? Whoever did this obviously was very clever, but I never would imagine this little code could do this much and make that many changes. So anyway, that's our discussion of recursion. In the next video or two, we'll have to rely very heavily upon using it, and really won't have a decent alternative to not using it. So we'll pick up on that in, I guess, the next video.